Classical physics stands as one of humanity's greatest intellectual achievements. It represents the very first complete framework through which we learned to describe the universe with precision, prediction, and mathematical beauty. Long before we ever imagined atoms, photons, or quantum fields, classical physics was the tool that allowed us to understand why things move, how forces shape motion, and how energy flows from one place to another. It is the discipline that carried humanity from mystery to mastery. To explain this keynote in a deep, documentary-style narrative, we return to the world that existed before the quantum revolution, a world where the laws of nature seemed fixed, stable, and unshakable. In the late 17th century, Isaac Newton crafted a picture of the universe that felt almost magical in its clarity. His laws of motion and universal gravitation unified earth and sky under the same rules. The apple falling from the tree and the moon orbiting the earth were no longer separate mysteries, they were governed by the same invisible force. Newton's equations were so precise that one could predict the path of a comet centuries into the future. This predictability shaped the Western mind's view of reality. The universe was a giant clockwork machine, perfectly ordered and completely comprehensible. As time passed, other giants added their brilliance to this classical foundation. James Clerk Maxwell revealed the elegant equations of electromagnetism, showing that light was a traveling electromagnetic wave. Galileo described motion with unprecedented clarity, while Kepler discovered the laws of planetary motion. Their discoveries stitched together a world where everything seemed continuous, smooth, and governed by absolute laws. Classical physics was not just a set of equations. It was a world view. It told us that if one knew all the forces and all the positions of every particle, one could predict the entire future of the universe. Nothing was uncertain, nothing was hidden, nothing was random. This created a feeling of intellectual security. For the first time in history, humans believed that the universe was understandable in a complete and final way. The behavior of falling objects, flowing rivers, orbiting planets, vibrating strings, and moving machines all followed the same clear principles. Classical physics became the engine behind the Industrial Revolution. It gave birth to engineering, mechanics, architecture, modern transportation, and countless technologies that changed human civilization. Steam engines, bridges, railways, ships, and electrical generators all relied on classical laws to function. But classical physics offered more than technological power. It offered philosophical comfort. It suggested that the universe behaves logically and that human reason can uncover its secrets. It painted a picture of nature as elegant, deterministic, and obedient to mathematical rules. In this world view, if something happened, there was always a cause, and that cause could be measured, calculated, and understood. This was the scientific dream, a universe without surprises, yet classical physics also had its limits. As scientists pushed deeper into the microscopic world, strange contradictions appeared. Heated objects released radiation in unexpected patterns. Electricity behaved in ways that didn't match classical predictions. Matter seemed to lose its classical form when observed at atomic scales. Still, before these cracks were noticed, classical physics had already built the foundation that future theories, including quantum physics, would stand upon. Every law of quantum mechanics, every modern theory, and every new discovery still traces its roots back to classical thinking. Even today, when scientists describe incredibly small particles or unimaginably large galaxies, they often begin with classical models. Only when those models fail do they switch to quantum or relativistic corrections. Classical physics remains the starting language of science because it is intuitive, reliable, and deeply embedded in the way reality appears to us. Most of what humans experience daily, walking, driving, throwing a ball, building a structure, flowing water, flying airplanes, belongs fully to the classical world. This world is not wrong, it is simply a large-scale limit of deeper quantum rules. Classical physics is the visible, tangible expression of the underlying quantum universe. It is the bridge that connects human experience with the invisible atomic realm. In documentary terms, classical physics is the canvas upon which the quantum world paints its deeper truths. Without it, the quantum revolution would have been incomprehensible. It provided the first stable understanding of forces, motion, and energy, allowing later scientists to recognize when those laws began to break down. The pioneers of quantum theory, Planck, Einstein, Bohr, Heisenberg, were all trained in classical physics. They used its language, its logic, and its equations as stepping stones toward the new world of quanta. Thus, the first keynote reminds us that classical physics is not just an old chapter in scientific history. It is the foundation of everything that came after. It is the first bridge between human curiosity and the laws of nature. It remains valid, powerful, and essential for understanding reality at the scale where life unfolds. Classical physics taught us how to see the world with clarity. And without that clarity, the mysteries of the quantum realm might never have been discovered at all. Quantum physics arrived like a storm that no one expected, challenging the comfortable certainty built by classical laws. For centuries, scientists believed that the universe behaved smoothly and predictably, that every motion, every force, and every event could be explained with mathematical precision. Classical physics appeared complete, flawless, and universally valid. But as researchers began to explore the world at extremely small scales inside atoms, near the limits of energy, and within the structure of matter itself, they discovered behaviors that no classical idea could explain. This keynote highlights the moment when humanity came face to face with a new reality, a universe where the rules change dramatically as we move from the visible world to the microscopic one. The earliest hints of this strange new world emerged in the late 1800s. Scientists studying glowing metals, electric discharges, and atomic spectra found that energy did not flow continuously as classical theory predicted. Instead, it appeared in sudden jumps, in discrete packets that had no place in classical reasoning. Max Planck took the first daring step by proposing that energy comes in small, indivisible units called quanta. Though he introduced this idea reluctantly, it cracked open a door that classical physics had kept tightly shut. Once the door opened, the mysteries rushed in. Einstein soon pushed it wider by explaining light as tiny particles called photons, not merely waves as classical electromagnetism described. This idea was revolutionary because it suggested that the very nature of light depended on circumstances, sometimes wave-like, sometimes particle-like. In the classical world, something could not be both. In the quantum world, it could. This dual behavior challenged centuries of scientific logic and signaled that a new framework was needed, one that could accommodate nature's unexpected flexibility. As experiments grew more precise, the quantum puzzle deepened. Electrons behaved like ripples, spreading out through space, yet they also struck a detector like discrete particles. Atoms emitted very specific colors of light, not a continuous rainbow. Small particles tunneled through barriers as if they were ghosts. Even stranger, the simple act of measuring these particles seemed to change their behavior. None of this made sense under classical rules. Those rules assumed that objects had definite positions, definite energies, and definite paths. Quantum experiments showed that, at tiny scales, nature does not commit to any one state until the moment of observation. This contradiction between expectation and reality forced scientists to rethink the foundations of physics. The classical description of the universe as orderly and predictable was still valid for everyday life, but at the atomic level, a deeper and far more mysterious set of rules took over. The new quantum laws did not merely modify classical physics, they replaced its most fundamental ideas. Particles could exist in multiple states at once, a concept known as superposition. They could be entangled, sharing information instantaneously across vast distances, defying classical understandings of space and time. Probability replaced certainty. The future could no longer be predicted with perfect accuracy. Only likelihoods could be calculated. For the scientific community, this shift was not just a technical correction, it was a philosophical earthquake. Quantum physics forced humans to accept that the universe was not completely deterministic. The idea that nature behaves in fixed, predictable ways collapsed at the smallest scales. Instead, reality became a landscape of potentialities where only measurement gives shape to what is real. This was profoundly unsettling, but also deeply beautiful, revealing layers of complexity hidden beneath the surface of the classical world. Conflict between classical intuition and quantum behavior shaped decades of scientific debate. Some researchers embraced the new ideas with excitement, others resisted them fiercely. Einstein himself, though he helped create the early quantum theory, could not accept the randomness at its core. He famously argued that God does not play dice. But experiments repeatedly confirmed that quantum rules were not illusions. They accurately described atoms, electrons, photons, and the very structure of matter. Classical physics was not wrong, it was simply incomplete. It described the world we can see, touch, and measure with our senses. Quantum physics described everything beneath that surface, where nature dances to a different rhythm. As understanding grew, this strange quantum behavior became the foundation of modern science and technology. Transistors, lasers, computer chips, LEDs, and MRI machines all rely on principles that classical physics could never explain. Quantum mechanics did not replace classical laws in daily life, but it extended them, revealing why classical physics works so well at large scales and why it breaks down at small ones. The quantum world is the engine behind the classical world, even if its behavior is hidden from us. This keynote reminds us that scientific progress often begins where old ideas fail. The rise of quantum physics showed that the universe is far richer, more mysterious, and more intricate than classical thinkers ever imagined. Classical physics gave us order, quantum physics gave us depth. Together, they form a layered understanding of reality where the familiar world emerges from a realm that is anything but familiar. The challenge to classical physics was not a destruction, but an expansion, pushing human knowledge into places that once seemed unreachable. At the boundary between the world we see and the world we cannot see lies a remarkable meeting point, a soft and invisible transition where the laws of classical physics begin to fade and strange rules of quantum mechanics slowly take over. This keynote explores that thin region where both worlds coexist, shaping everything from the way atoms form to the way planets move, and revealing how nature blends two seemingly opposite realities into one continuous universe. In documentary style, we travel into this frontier, a place where the familiar ends and the extraordinary begins. In our everyday experience, the world behaves in predictable ways. Balls bounce, waves crash, machines operate, and planets orbit according to classical rules defined by Newton, Maxwell, and other pioneers. Their equations work so well that we can launch rockets across the solar system or design skyscrapers that stand for decades. But as we shrink our view down to the atomic scale, the classical picture begins to crack. The motions become uncertain, the locations blur, and energy no longer flows smoothly. What appears solid becomes mostly empty space. The neat pathways of classical particles transform into floating clouds of probability. But between these two extremes lies a fascinating zone where neither picture is entirely correct. This is the bridge between the classical and quantum worlds. This bridge is not a physical place, it is a scale, a size range, where objects are too small to ignore quantum effects, but too large to behave purely quantum. A dust particle drifting in a beam of sunlight, a grain of pollen floating in water, or even a tiny droplet vibrating under high frequency light all sit within this mysterious region. They obey classical motion in some ways, but show hints of quantum behavior in others. Scientists discovered this bridge when they observed small objects behaving unpredictably under magnification. Instead of moving smoothly, they jittered, hopped, and vibrated as if being pushed by invisible forces. This was the first evidence that the microscopic world influences the macroscopic, one more directly than classical physics had assumed. In this transitional realm, nature reveals that its rules are not divided but layered. Classical behavior is not something separate. It is an emergent property rising out of countless quantum interactions. When a particle is small enough, it can exist in superpositions, being in multiple states at once. But as particles become larger and interact with air molecules, light, and their surroundings, these superpositions quickly vanish. The environment washes away the quantum weirdness, forcing objects to behave classically. This fading of quantum behavior is known as decoherence, and it is the natural process that creates the bridge between the two realms. It is why a single electron can behave like a wave, but a grain of sand cannot. The larger an object becomes, the more its environment collapses its quantum possibilities into a single classical reality. Still, the bridge is not one way. Even large-scale phenomena sometimes reveal subtle quantum fingerprints. Superconductors lose all electrical resistance due to quantum effects acting collectively across millions of electrons. Superfluids glide without friction, defying classical expectations. In modern laboratories, scientists have even cooled tiny mechanical objects visible to the human eye into pure quantum states, making them vibrate in ways no classical object should. These achievements prove that quantum behavior never disappears. It only hides beneath layers of environmental noise. When those layers are stripped away, the bridge reveals itself again. The most striking aspect of this transitional zone is how smoothly nature shifts between behaviors. There is no sudden line, no sharp boundary where classical rules stop and quantum laws begin. Instead, the change resembles a sunrise. Quantum darkness gradually brightens into classical daylight. At atomic scales, particles behave almost entirely quantum. At human scales, almost everything behaves classical. Between them lies a wide region where the two worlds blend, a mixing of probabilities and certainties, of waves and particles, of randomness and law. This blending teaches us an important lesson. The universe is not divided into parts, but unified across scales. What seems like two different worlds are simply two perspectives on one continuous reality. Understanding this bridge has allowed scientists to design advanced technologies that rely on both worlds at once. Quantum tunneling powers the chips inside modern electronics, yet those chips function within classically engineered devices. Lasers arise from quantum principles but are used in classical machines. Even biological systems like photosynthesis use quantum effects to transfer energy with extraordinary efficiency. Life itself seems to take advantage of this blended zone, using quantum principles quietly inside classical bodies. In the grand story of physics, this transitional bridge represents a deeper truth. The laws of the universe are interconnected. Classical physics describes the world as we experience it. Quantum physics describes the world as it truly is beneath the surface. And between them is a smooth, seamless transition that reminds us that nature is far more unified than our divisions suggest. This keynote highlights that unity, showing that the bridge between classical and quantum worlds is not just a scientific concept, but a profound insight into how reality organizes itself from the smallest atoms to the largest galaxies. Classical laws remain astonishingly accurate at large scales, and this keynote reveals why the universe we experience every day behaves with such remarkable stability and predictability. In a documentary tone, we step into a world that feels familiar. The world of falling objects, flowing rivers, spinning planets, and moving machines. These are the phenomena described elegantly and powerfully by classical physics. While quantum mechanics rules the realm of atoms and subatomic particles, classical laws continue to dominate everything from the size of a grain of sand to the motion of galaxies. This keynote explores why classical ideas remain not only valid but essential for understanding the macroscopic universe. When scientists first constructed the classical framework, they believed they were uncovering universal truths laws that applied everywhere under all conditions. Newton's laws of motion allowed them to calculate the trajectories of planets with astonishing precision. Maxwell's equations unified electricity and magnetism into a single, elegant theory. Thermodynamics revealed how heat, energy, and entropy governed the behavior of large systems. These classical laws were so successful that they became the backbone of engineering, astronomy, and everyday science. And even after quantum physics emerged, the classical framework did not crumble. Instead, it remained fully accurate for the vast majority of the physical world. The reason classical laws work so well is that at large scales, the chaotic and probabilistic behavior of individual particles averages out. A single gas molecule may move unpredictably, but a room filled with billions of those molecules behaves in smooth, predictable patterns that classical thermodynamics can describe. An electron may exist in a superposition, but a baseball made of trillions of interacting particles never does. The randomness of the microscopic world dissolves into the stability of the macroscopic one. This phenomenon is what allows classical laws to remain accurate over enormous distances and timescales. When we look at a pendulum swinging, we do not see the quantum jitter of atoms. We see a regular, rhythmic motion. That is not because quantum mechanics stops working, but because the influence of quantum effects becomes negligible at larger scales. In fact, classical laws emerge naturally from quantum laws when enough particles are involved. This process, known as the correspondence principle, ensures that classical physics is not an outdated theory but a large-scale expression of the deeper quantum rules. In a sense, classical physics is the shadow cast by the quantum world, stable, predictable, and smooth. Even on cosmic scales, classical laws hold extraordinary power. The orbits of planets, the rotation of galaxies, the motion of stars, and the paths of comets all follow classical gravitational laws. Astronomers can predict solar eclipses centuries into the future using classical models alone. Engineers rely on classical mechanics to construct bridges, aircraft, satellites, and skyscrapers. A car's engine, a ship's navigation, and an airplane's flight path all depend on classical mathematics. These systems are far too large and too interconnected for quantum effects to influence their motion in meaningful ways. Yet the accuracy of classical laws is not due to their completeness, but to the scale at which they operate. Quantum physics is the foundation, but classical physics is the visible manifestation. When objects become large enough and interact strongly with their surroundings, quantum superpositions collapse almost instantly through a process called decoherence. This means a macroscopic object cannot be in two states at once the way an electron can. The world we see is locked into definite outcomes. That is why everyday objects have clear positions, clear speeds, and clear behaviors. The overwhelming interactions with the environment prevent quantum uncertainty from surviving long enough to influence large-scale motion. The forces that hold the world together, gravity, electromagnetism, friction, tension, can all be described with classical equations that work perfectly well at human scales. The classical approximation is so accurate that scientists use it to model earthquakes, weather patterns, ocean currents, and even the dynamics of spacecraft exploring distant planets. Quantum mechanics is unnecessary for these tasks because its effects vanish into insignificance when trillions of particles interact simultaneously. The persistence of classical laws also reveals something profound about the nature of reality. The universe is not built in separate layers but in nested scales. The quantum world forms the microscopic foundation, while the classical world is its macroscopic expression. One does not replace the other. Instead, they complement each other. Classical laws show us what emerges when countless quantum processes combine into a single, unified behavior. This is why classical physics remains one of the most powerful and accurate tools ever created, even in the age of quantum science. This keynote reminds us that although quantum mechanics may be the more fundamental theory, classical physics is the one that shapes the world we live in. It governs the movement of planets, the beating of waves, the rising of mountains, and the rotation of the Earth. The accuracy of classical laws at large scales is not an accident but a natural consequence of how complexity organizes itself. In the documentary story of science, classical physics stands as the reliable narrator of the macroscopic world, a narrator whose voice remains clear and trustworthy even as we explore the deeper mysteries revealed by quantum mechanics. Quantum rules dominate at microscopic scales, creating a universe that behaves in ways far beyond human intuition. And this keynote guides us deep into that hidden realm. In a documentary style, we journey into the heart of matter, into the world of atoms, electrons, and subatomic particles, where the familiar laws of classical physics no longer apply and where the rules of existence are rewritten entirely. Here, the universe expresses its most fundamental behavior, revealing patterns and principles that shape everything we see, yet remain invisible to everyday experience. When scientists first probed the microscopic world, they expected classical physics to continue working as it always had. They imagined that atoms would behave like tiny planets orbiting a central sun, that energy would flow smoothly, and that particles would follow clear, predictable paths. But as the tools of observation grew more powerful and precise, those expectations shattered. Inside atoms, particles refused to obey classical logic. They did not stay in one place. They did not follow one path. Instead, they moved in ways that were probabilistic, discontinuous, and profoundly mysterious. This was the beginning of a revolution, a realization that at microscopic scales, the universe operates by an entirely different set of rules. One of the most striking discoveries was that particles at small scales behave both like waves and like particles. An electron, for example, spreads through space like a ripple on water, yet hits a detector as a single, localized point. Light behaves the same way. This dual nature is impossible to describe using classical physics, which demands that something must be either a wave or a particle, but never both. At the quantum level, however, nature allows this contradiction to exist peacefully. It is the first sign that the microscopic universe is governed by a logic far removed from our everyday experience. As scientists explored deeper, they found that particles do not even possess definite positions or velocities unless they are measured. Instead, they exist in a cloud of possibilities, a superposition of states. Only when we observe them does the cloud collapse into a single reality. Before the observation, the particle is not here or there. It is in many places at once. This idea is not metaphorical. It is a measurable fact confirmed in countless experiments. Classical physics could never allow such a phenomenon, but quantum rules thrive on it. In the microscopic world, probability replaces certainty, and measurement becomes an active part of reality, not a passive observation. Another extraordinary quantum rule is entanglement, a phenomenon so strange that Einstein called it spooky action at a distance. Two particles can become linked in such a way that whatever happens to one instantly affects the other, no matter how far apart they are. Classical physics insists that nothing can influence something else faster than the speed of light. But entanglement defies this limit not by sending signals, but by binding the fates of particles together in ways that classical thinking cannot explain. This entanglement is not rare or exotic. It is a fundamental feature of microscopic behavior. Quantum tunneling is yet another rule that dominates the microscopic domain. Particles can pass through barriers that they do not have enough energy to overcome. Classically, this is impossible, like a ball rolling up a hill and appearing on the other side without ever going over the top. But in the quantum world, the wave nature of particles allows them to slip through obstacles. This phenomenon is essential for many natural processes, including nuclear fusion inside the Sun, and it forms the basis of technologies such as scanning tunneling microscopes and flash memory. At microscopic scales, even the concept of energy becomes quantized. Electrons within an atom cannot possess just any amount of energy. They must occupy specific, discrete levels. These energy steps give rise to the spectral lines of elements, the chemical behavior of atoms, and the entire structure of the periodic table. Classical physics expected smooth, continuous behavior. Quantum rules delivered a universe of precision and limits where nature distributes its energy in exact packets. All of this strange behavior becomes hidden at larger scales because quantum effects tend to wash out when trillions of particles interact with each other and with their environment. But at the small scale, inside atoms and molecules, these rules reign supreme. They shape the structure of matter, govern the interactions of particles, and determine the behavior of every chemical reaction. Every breath we take, every spark of electricity, every color we see is guided by laws that classical physics could never hope to describe. Quantum rules dominate the microscopic world not because the universe is divided, but because the small-scale structure of reality is inherently probabilistic and wave-like. Classical physics emerges later as a kind of approximation when many quantum systems combine to form stable, predictable behavior. But the quantum world remains the foundation upon which everything rests. It is the engine of the universe's smallest processes and the source of all matter's complexity. In this keynote, we see that the microscopic world is not simply smaller, it is different. It operates by principles that challenge our understanding, stretch our imagination, and reveal that the fabric of reality is woven from probabilities, waves, and entanglement. The rules that dominate the quantum realm remind us that beneath the calm surface of everyday life lies a universe far more dynamic, mysterious, and extraordinary than classical physics ever imagined. At the heart of modern physics lies a remarkable realization. Our world is not built from smooth, continuous flows of energy as classical physics once assumed, but from tiny, indivisible packets called quanta. This keynote explores the profound idea that energy itself is quantized, a discovery that reshaped our understanding of nature and opened the door to the quantum revolution. In a documentary style, we travel back to the early 20th century when scientists first confronted a mystery that classical laws could not decode, and we follow the path that led to one of the most important breakthroughs in human knowledge. For centuries, physicists believed that energy behaved like a continuous substance, capable of being divided into infinitely small amounts. This assumption worked well for large systems heating water, burning wood, or generating electricity, but at extremely small scales, this classical picture began to break down. The spark that exposed this failure came from an unlikely source, the glow of heated objects. When scientists studied the color and intensity of light emitted by hot materials, they expected to find smooth, continuous energy behavior. Instead, they discovered something far stranger. Energy was not being released in a smooth flow, but in discrete jumps. This puzzle, known as the blackbody radiation problem, became the crisis point for classical physics. No existing theory could explain why objects glowed the way they did. Some equations predicted infinite energy output at high frequencies, an absurd and impossible result. Classical physics had hit a wall. It was Max Planck who took the bold step that would change everything. In 1900, he proposed a radical solution. Energy could only be absorbed or emitted in small, fixed quantities, not continuously. He called these units quanta. Planck did not fully believe the idea at first. He considered it a mathematical trick, but nature quickly proved him right. Einstein expanded this breakthrough by applying the quantum concept to light itself. He argued that light was not just a wave, but was also made of particles, each carrying a single quantum of energy. This idea explained the photoelectric effect, why light can knock electrons out of metal only when it reaches a certain frequency. Einstein's insight revealed a deeper truth. Energy is fundamentally granular. It exists in steps, not slopes. This was the birth of quantum physics. As scientists explored further, they found that quantization was not limited to light. Electrons within atoms could only possess specific, fixed energy levels. They could jump from one level to another, releasing or absorbing energy as quanta. This explained why atoms emit very specific colors of light, and why the structure of matter is stable. Without quantization, electrons would spiral into the nucleus, and atoms would collapse. Quantum energy levels created order from chaos, giving atoms their durability and the universe its structure. This quantized behavior is not a rare event. It governs every microscopic process. Chemical reactions occur because electrons jump between quantized energy states. Lasers work by stimulating electrons to release identical quanta of light. Even modern electronics rely on quantized energy to control how electrons move through semiconductors. The entire universe at its smallest scales behaves like a finely tuned staircase. Particles can only occupy certain steps, never the spaces between them. Quantization also gave rise to the wave function, a mathematical description that assigns probabilities to where particles might be or how much energy they might have. Instead of infinite possibilities, the quantum world offers a limited and precise menu of allowed states. This discreteness is why atoms form stable bonds, why matter does not collapse, and why the universe does not behave like an undefined, chaotic soup. In the quantum realm, nature chooses from fixed options, not continuous ranges, yet this idea remains deeply counterintuitive. Classical physics teaches us to think of energy like a smooth fluid that can be split endlessly, but the quantum world says otherwise. Energy behaves more like currency. You cannot spend half a penny if pennies are the smallest unit available. In atoms, the smallest unit of energy is the quantum, and nothing smaller is allowed. This simple idea has staggering consequences. It forces electrons into defined shells. It determines how heat flows at microscopic scales. It shapes the colors we see, the conductivity of metals, and even the behavior of the sun. The universe becomes a giant orchestra, where each particle plays only certain allowed notes. The concept of quantized energy also highlights a deeper truth. Classical physics is not wrong, but incomplete. At large scales, the steps between quantum energy levels become so tiny that they appear continuous. That is why classical physics works so well for everyday experiences. But when we zoom into microscopic dimensions, the steps become noticeable, and the quantum nature of energy takes full control. In this keynote, energy quantization stands as one of the most important pillars connecting the classical and quantum worlds. It marks the point where classical assumptions failed and where a new, deeper understanding emerged. Without quantization, atoms would not exist, chemistry would not function, and life itself would be impossible. It is the quiet, hidden architecture of reality, an invisible set of rules that governs every jump, every transition, and every transformation in the microscopic universe. The discovery of quantized energy is a reminder that nature's fundamental structure is not smooth but granular, not continuous but crafted from precise, indivisible building blocks. This idea reshaped physics forever, revealing that the universe we experience is only the large-scale shadow of a much more discrete, finely layered quantum world. The story of the bridge between classical and quantum worlds would be incomplete without understanding the early cracks that appeared in the classical picture itself, long before quantum mechanics officially arrived. This keynote dives into one of the most important turning points in physics, the moment when scientists realized that classical laws, however elegant and powerful, simply could not describe the universe at every scale. It was a quiet but profound crisis, unshakable truth. Forgive him your snarings. What emerged from this crisis was not just a new equation or a modified formula, but the birth of an entirely new world view, one that introduced concepts unimaginable in the deterministic universe of Newton. This shift did not happen overnight. It unfolded through subtle contradictions, experimental puzzles, and theoretical dead ends that classical physics could not resolve. Each new anomaly was like a small crack in a mighty dam. Classical ITDESSCRIPTIO, what you of nature once thought complete limit. The classical world, you had been astonishingly successful. Newton's laws explained planetary motion, falling apples, tides, and the very structure of the solar system. Maxwell's equations unified electricity, magnetism, and light, revealing an elegant electromagnetic reality woven into the fabric of space. Thermodynamics explained heat, engines, and energy conservation on a grand scale. To many physicists of the 19th century, science seemed nearly complete. All that remained, in their view, were details, refinements of equations, more precise measurements, perhaps minor corrections. But beneath this confidence lay small mysteries that did not fit into the classical frame. They appeared harmless at first, but their implications would eventually prove revolutionary. One of the earliest cracks emerged from the study of heat radiation. Classical physics predicted that a hot object should emit infinite energy at short wavelengths, a problem soon known as the ultraviolet catastrophe. This prediction made no physical sense. No object in the universe behaves this way, yet according to classical equations, nature should. Scientists tried adjusting constants, modifying formulas, even inventing hypothetical mechanisms, but nothing worked. It was a dead end from the classical perspective. This single problem revealed a startling truth. Classical physics could not describe energy at extremely small scales. Something deeper was missing. Another mystery appeared in the stability of atoms. According to classical electromagnetic theory, an electron orbiting a nucleus should continuously lose energy and spiral inward, collapsing the atom in a fraction of a second. But atoms clearly do not collapse. They are stable, structured, and foundational to matter itself. The classical view predicted a universe in which atoms should not exist. Again, classical laws failed to explain the most basic units of reality. More puzzles emerged in the behavior of light. Experiments like the photoelectric effect showed that light could behave like a particle, delivering discrete packets of energy. Classical wave theory could not account for this behavior. Light, which had been understood for centuries as a smooth, electromagnetic wave, suddenly exhibited actions that defied every classical expectation. Similarly, blackbody radiation, atomic spectra, and the behavior of electrons in metals all pointed toward the same conclusion. Nature was quantized, fragmented into packets, levels, and probabilities that classical thinking could not describe. Each of these anomalies pushed the boundaries of the classical world until the framework itself began to bend. Slowly, physicists recognized that they were not dealing with minor inconsistencies, but with fundamental contradictions. The classical universe, a world of certainty, continuity, and smooth causality, could not survive in the realm of the very small. The deeper scientists went, the more the classical laws unraveled. But these contradictions did not destroy classical physics. Instead, they revealed the threshold where its power ended and something new had to begin. This realization marked one of the most dramatic conceptual transitions in the history of science. Human understanding of nature was forced to evolve. Physicists had to accept that particles could behave both like waves and like matter, that energy could be emitted in discrete quanta, that electrons could occupy stable allowed levels rather than classical orbits, and that certainty itself was not a fundamental feature of the universe. Probabilities replaced determinism, fields replaced forces, waves existed not in space, but in abstract probability landscapes. It was not just a new theory, it was an entirely new language for describing the universe, and yet this new quantum world did not erase classical physics. It revealed that classical laws are approximations accurate and powerful on large scales, but incomplete in the microscopic world. Classical physics survives as the visible surface of a deeper quantum reality. The crisis of classical physics did not mark an end, but a transformation. Nature did not abandon the classical world. It expanded beyond it. The bridge between classical and quantum realms began as a collapse of certainty, but it ultimately evolved into a unified understanding that continues to shape modern science and technology. The breakthroughs that emerged from these early inconsistencies now power lasers, computers, MRI machines, GPS systems, and the entire digital world. The crisis that once threatened physics became the very foundation of its greatest achievements. As physicists continued to uncover the strange behavior of nature at tiny scales, a remarkable realization began to emerge. The bridge between the classical and quantum worlds did not lie in choosing one model over another, but in understanding how both pictures could coexist. This keynote explores the dawn of a new idea wave, particle duality, an idea that connected two seemingly incompatible realities into one coherent picture of nature. It was a concept that defied classical intuition, yet connected the familiar macroscopic world to the mysterious quantum realm with a logical thread that science had never seen before. This transformation began quietly, almost reluctantly, as experiments forced scientists to re-examine ideas that had stood unchallenged for centuries. In the classical world, waves and particles were distinct categories. Waves spread out, interfered, and overlapped, while particles traveled in straight lines, collided, and occupied specific points in space. But the quantum world shattered this neat separation, revealing that the fundamental building blocks of nature could behave as both waves and particles, depending on how they were observed. This was not merely a modification of classical physics. It was a revolution in how we understand reality. Light was the first phenomenon to expose this dual nature. For centuries, physicists had debated whether light was a stream of particles or a continuous wave. Newton had argued for particles, while Huygens championed waves. Maxwell's equations later confirmed that light was an electromagnetic wave, and this wave picture reigned supreme. But the discovery of the photoelectric effect changed everything. When light struck certain metals, it ejected electrons with energies that depended not on the intensity of the light, but on its frequency. Classical wave theory could not explain this behavior. The only explanation that worked came from a daring idea. Light must come in discrete packets of energy, later called photons. In that moment, light regained its particle identity, but without losing its wave nature. It could behave as both, and neither description alone was sufficient. This duality was the first sign that classical categories were too narrow to describe the true nature of the universe. But the real shock came when matter itself, solid, tangible matter, showed the same dual behavior. Louis de Broglie proposed that if light, a wave, could behave like a particle, then particles like electrons might also behave like waves. At first, the idea seemed outrageous. Particles had mass, position, and momentum. How could they also be waves? Yet experiments soon confirmed de Broglie's prediction. Electrons, when passed through a crystal or a double-slit apparatus, produced interference patterns that only waves should create. These tiny particles, which classical physics treated as miniature billiard balls, showed behaviors that no classical equation could describe. They spread, diffracted, and interfered with themselves, even when fired one at a time. It was as if each electron traveled through multiple paths simultaneously, creating a pattern from probabilities rather than certainties. The classical boundary between waves and particles dissolved, forcing science to adopt a new language to describe nature. This duality did not mean that particles simply switch between wave behavior and particle behavior. Instead, it meant that both descriptions are incomplete without the other. An electron does not stop being a particle when it behaves like a wave. It simply reveals a deeper nature that classical physics cannot capture. The same is true for photons, atoms, and even large molecules. Wave-particle duality became one of the cornerstones of quantum mechanics, providing the crucial link between the predictable motions of classical objects and the probabilistic patterns of quantum world. It showed that classical behavior is not a separate phenomenon, but an emergent property of quantum rules when applied to large systems. The bridge between the classical and quantum worlds became clearer through this duality. At large scales, wave effects often cancel out or become too small to detect, allowing objects to behave like solid particles following Newton's laws. A baseball, for example, has a wavelength so incredibly tiny that it behaves purely like a particle. But at small scales, atoms, electrons, photons, the wavelength becomes significant, and classical physics breaks down. What seems like two different worlds is actually one world viewed at different resolutions. Wave-particle duality provided the first real proof that classical physics is not wrong. It is simply incomplete. It emerges from quantum principles when applied to everyday scales, where wavelengths shrink and probabilities average into predictable behavior. The implications of this duality transformed not just theory but technology. Electron microscopes use the wave nature of electrons to reveal structures far smaller than light can resolve. Lasers operate by manipulating quantum states of photons. Semiconductor devices rely on electrons behaving like waves in confined spaces. Every digital device, from smartphones to computers, is built upon quantum behaviors rooted in wave-particle duality. The modern world runs on the very principles that once seemed impossible within classical physics. But beyond its practical impact, wave-particle duality challenged humanity's understanding of reality itself. It showed that nature cannot be forced into rigid categories and that observation plays a role in shaping the outcome of quantum events. The universe, at its core, is not simply made of particles or waves. It is made of entities that transcend classical labels. Wave-particle duality stands as one of the most elegant and profound connections ever discovered. A bridge that links the certainty of the classical world to the possibilities of the quantum realm. It reveals a universe richer and stranger than anyone had imagined, yet unified by principles that operate consistently across all scales. As the 20th century unfolded, scientists found themselves facing a profound puzzle that lay at the very heart of the new quantum world. How does something that behaves like a wave also appear as a particle the moment we measure it? This mystery, known as wave-function collapse, became one of the most fascinating and unsettling bridges between the classical and quantum worlds. It suggested that the act of observing nature does more than reveal what is already there. It actually influences what reality becomes. This idea was deeply disturbing to physicists raised in the classical tradition, where objects existed with definite properties independent of anyone watching. Yet, every experiment seemed to show that, in the quantum realm, observation played an unexpectedly active role. To understand this strange behavior, imagine an electron traveling through space. According to quantum mechanics, it does not move like a tiny ball with a specific trajectory. Instead, it spreads out like a wave, occupying many possible positions at once. This wave is not a physical ripple in water or air. It is a mathematical wave representing probabilities. The probability that the electron might be here or there or somewhere else entirely. As long as no one observes it, the electron exists in this hazy cloud of possibilities, a blend of many potential realities layered on top of one another. But the moment a measurement is made, when someone tries to detect where the electron actually is, that smooth, spread-out wave of possibilities suddenly collapses into one specific outcome. The electron appears in one location, and all the other possible positions vanish instantly. It is as if nature refuses to reveal itself fully until the act of measurement forces it to make a choice. This behavior contradicts every classical instinct. In the classical world, objects have positions, speeds, and paths that exist whether or not someone is watching. A ball rolling down a hill does not wait for an observer before deciding where it is, but in the quantum world, particles behave as if they remain undecided until measured. This raised uncomfortable questions. Does the act of observation create reality? Is the observer just another physical system interacting with the quantum world? Or does consciousness play some role? Physicists debated these questions passionately, and no consensus emerged. What was clear, however, was that wave-function collapse was an essential part of the bridge between the microscopic quantum world and the macroscopic classical world. Experiments made this even more dramatic. In the famous double-slit experiment, a single electron fired at two slits creates an interference pattern, proving it behaves like a wave that passes through both slits at the same time. But if a detector is placed at the slits to see which path it takes, the interference pattern disappears. The electron suddenly behaves like a classical particle, choosing one path or the other. The very act of measuring destroys the wave behavior. It is a stunning illustration of how the quantum world changes form when observed. The experiment shows two realities, one where particles behave like waves when unobserved, and one where they behave like particles the moment we try to watch them closely. This dual nature is not a flaw in quantum theory. It is one of its most fundamental characteristics. Physicists realized that wave-function collapse acts like a boundary, a point where quantum possibilities condense into classical reality. It is the moment when the strange, probabilistic world of superpositions transitions into the definite outcomes we see in everyday life. Without collapse, we would live in a universe where objects could be in multiple places at once, where cause and effect would blur into probabilities, and where the classical world would dissolve into waves of uncertainty. Collapse is what gives the macroscopic world its stability. It explains why cars, trees, mountains, and people follow predictable behaviors, even though they are ultimately made of quantum particles. When billions of particles interact, their individual wave functions collapse rapidly and constantly, creating the illusion of continuity and certainty. The classical world emerges not because quantum rules stop working, but because collapse becomes the dominant process. But collapse remains one of the most mysterious aspects of modern physics. Does it happen instantaneously? What triggers it? Does the universe choose an outcome at random, or is there some hidden mechanism behind the scenes? Several interpretations attempted to explain it. The Copenhagen interpretation argued that collapse is a fundamental rule of nature. The many worlds interpretation claimed that collapse never truly happens. Instead, the universe splits into multiple branches, each containing one possible outcome. Other theories suggested that collapse is triggered by environmental interactions, or that it is tied to gravity itself. No one knows which interpretation is correct, but all agree that collapse is essential to understanding how the quantum world gives rise to the classical world we experience. Wave-function collapse became a conceptual bridge, even if not a fully understood one. It marked the boundary where quantum behavior dissolves into classical certainty, where probabilities condense into definite outcomes, and where the hidden world of superpositions becomes the tangible world of everyday experience. It represents one of the most profound ideas in science, that the universe behaves differently when probed at its deepest levels, and that our classical intuition captures only the surface of a much richer, more mysterious reality. Entanglement is one of the most astonishing phenomena in the quantum world, a concept so strange that even the most brilliant minds struggled to accept it. It is a phenomenon that perfectly illustrates the subtle and profound bridge between classical and quantum realities. At first glance, classical physics offers a comfortable, predictable universe. Objects have properties, interactions are local, and causes lead to effects in a straightforward manner. But entanglement reveals that at the quantum level, particles can be intimately connected in ways that defy classical expectations, as if the universe itself maintains invisible threads linking separate objects across space and time. This quantum connection does not diminish as distance increases. Two entangled particles separated by light years remain correlated in ways that challenge our traditional notions of locality and causality. Entanglement is not a hypothetical concept. It is a measurable reality confirmed by countless experiments, and it forms one of the pillars of modern physics. The history of entanglement begins with the work of Einstein, Podolsky, and Rosen, who in 1935 presented a thought experiment that questioned the completeness of quantum mechanics. They imagined two particles created together and then separated by great distances. According to the quantum rules of superposition, each particle's state is uncertain until it is measured. However, when one particle is measured, the state of the other becomes instantly determined, no matter how far apart they are. Einstein famously referred to this as spooky action at a distance, because it appeared to violate the classical principle that nothing can influence another object faster than the speed of light. This thought experiment revealed a fundamental tension between quantum mechanics and classical intuition, highlighting the strange and non-local nature of the quantum world. Experiments conducted decades later confirmed that entanglement is real. By preparing pairs of photons or electrons in entangled states, scientists could measure one particle and immediately predict the behavior of its partner. These results consistently violated classical inequalities, known as Bell's inequalities, proving that no hidden classical variables could explain the correlations. In other words, entangled particles are not just correlated in a predictable manner like classical objects, they are fundamentally connected in a way that classical physics cannot replicate. This connection persists even when the particles are separated by vast distances, showing that quantum information operates according to rules profoundly different from classical communication. Entanglement challenges our intuitive understanding of reality. In the classical world, objects are independent. The state of one does not instantaneously determine the state of another far away. Entanglement demonstrates that, at the quantum level, particles can be inseparable in terms of their properties, even when spatially separated. The fate of one is intertwined with the fate of the other. This phenomenon blurs the line between locality and non-locality, showing that the universe is more interconnected than classical physics allows. It is a striking reminder that the classical world is an emergent approximation of a deeper quantum reality. The implications of entanglement are profound both philosophically and technologically. Philosophically, it forces scientists to rethink concepts of separateness, causality, and the very nature of information. It suggests that the universe is not merely a collection of independent objects, but a web of interdependent phenomena, where connections can exist even across vast distances. It reshapes our understanding of the boundary between observer and observed, showing that the act of measurement is not simply passive, but intimately linked to the system being observed. Technologically, entanglement has become the foundation of cutting-edge quantum applications. Quantum computing, for instance, relies on entangled qubits to perform calculations that classical computers cannot achieve efficiently. Quantum cryptography uses entangled particles to transmit information securely, guaranteeing that any eavesdropping attempt will be instantly detectable. Quantum teleportation, an experimental technique, uses entanglement to transfer the state of a particle from one location to another without moving the particle itself. These applications demonstrate that entanglement is not merely a curiosity or philosophical puzzle. It is a practical tool that allows humans to harness the hidden potential of the quantum world. Entanglement also illuminates the bridge between quantum and classical worlds. While macroscopic objects rarely display entanglement visibly, their underlying components, electrons, photons, atoms, are constantly interacting in ways that depend on quantum correlations. In small-scale systems, entanglement dominates behavior. As systems grow larger and interact with the environment, these quantum correlations become hidden, averaged out, or decohered, giving rise to the classical world we experience. The rules of classical physics emerge naturally from these underlying quantum connections. Entanglement, therefore, is a cornerstone in understanding why classical reality appears definite and local, even when its foundations are inherently probabilistic and non-local. Ultimately, entanglement demonstrates that the universe is both stranger and more elegant than classical physics suggested. It shows that separation does not always mean independence, that measurement can instantaneously influence outcomes across space, and that nature's fundamental structure is interconnected in ways we are only beginning to fully understand. It serves as a profound reminder that the classical world we navigate daily is built upon deep, invisible quantum relationships. Entanglement is more than a scientific principle. It is a bridge linking the familiar and deterministic classical reality to the counterintuitive, probabilistic, and interconnected quantum realm. It reminds us that reality itself is layered, with classical order emerging from quantum chaos, and that the universe is far richer than it appears at first glance. The story of quantum mechanics is incomplete without exploring the phenomenon of superposition, one of the most fundamental and fascinating principles that distinguish the quantum world from classical reality. Superposition is the idea that a particle can exist in multiple states at the same time, a concept that seems utterly impossible from the perspective of classical physics. In a documentary style, we travel into this hidden layer of reality, where the universe is not composed of fixed objects with definite properties, but of clouds of possibilities that exist simultaneously until observed. This principle forms a crucial bridge between the quantum and classical worlds, showing how the strange, probabilistic nature of tiny particles underlies the stable, predictable behavior we see in the macroscopic world. At its core, superposition challenges our most basic intuition. In classical physics, an object exists in one state at any given moment. A ball is either on the table or on the floor. It cannot be in two places at once. But in the quantum realm, particles behave differently. An electron in an atom, for example, does not occupy a single orbital or energy state. Instead, it exists in a combination of all possible states allowed by the quantum rules. It is only when a measurement is made, when someone observes the electron's position or energy, that the superposition collapses into a single outcome. Until that moment, the particle is not here or there, up or down, left or right. It is in a blend of all possibilities simultaneously. The experimental evidence for superposition is both subtle and compelling. In the double-slit experiment, a single electron passing through two slits creates an interference pattern, suggesting that it behaves as if it simultaneously passed through both slits at the same time. This cannot be explained by classical particles traveling through one slit or the other. The electron's behavior reveals that it exists in a superposition of paths, with the probability of landing in a particular location determined by the combination of all possibilities. The resulting interference pattern is a direct visual manifestation of superposition, showing that the quantum world does not adhere to a single, deterministic trajectory, but instead explores all potential outcomes at once. Superposition is not limited to position or momentum. It applies to energy levels, spin, polarization, and many other properties of particles. For instance, an electron's spin can be in a superposition of up and down until measured. Photons can exist in superpositions of polarization states. Even larger systems, under carefully controlled conditions, have been shown to exhibit superposition, with entire molecules occupying multiple states simultaneously. The principle is universal in the quantum realm, underlying the probabilistic nature of all microscopic interactions. Understanding superposition is key to connecting quantum behavior to the classical world. At small scales, superpositions are readily observed because particles interact minimally with their environment. But as systems grow larger, interactions with surrounding particles, air molecules, and light quickly destroy the coherence of superpositions. forcing the system into a single classical state. This process, known as decoherence, explains why macroscopic objects, such as chairs, cars, or people, appear to exist in definite states rather than superpositions. The classical world, stable and predictable, emerges naturally from the underlying quantum superpositions, which are constantly collapsing and averaging out over enormous numbers of particles. In this way, superposition is a bridge. It connects the probabilistic quantum realm to the deterministic classical world we experience. The implications of superposition extend far beyond philosophical curiosity. They are central to modern technology and cutting-edge science. Quantum computers exploit superposition by allowing qubits to exist in multiple states simultaneously. This capability enables a single quantum processor to explore many computational paths at once, performing calculations exponentially faster than classical computers for certain problems. Quantum cryptography relies on superposition to encode and transmit information securely, ensuring that any eavesdropping attempt disrupts the system and becomes immediately detectable. Even fundamental experiments in chemistry and biology rely on understanding how quantum superpositions influence the behavior of electrons and atoms, shaping chemical reactions, photosynthesis, and other processes at the molecular level. Superposition also forces scientists to rethink the nature of reality itself. It challenges the classical notion that properties exist independently of observation, and reveals a universe where possibilities are woven into the fabric of existence. Before measurement, particles do not have definite states. Instead, they exist as probabilities, as potentialities that are real in their own right. This insight has profound philosophical and scientific consequences, suggesting that certainty is an emergent property, not a fundamental one, and that the world we perceive is only a surface expression of a deeper quantum structure. Despite its counterintuitive nature, superposition is one of the most reliable and experimentally confirmed aspects of quantum mechanics. It underlies atomic structure, chemical bonding, and countless quantum phenomena. It explains why electrons occupy discrete energy levels, why light exhibits both wave and particle behavior, and why the universe, at its most fundamental level, is inherently probabilistic. Superposition is not an anomaly, it is a principle, a rule of nature that bridges the microscopic and macroscopic, connecting the quantum world of possibilities to the classical world of definiteness. In the grand story of physics, superposition represents both mystery and clarity. It reveals a universe far stranger than our senses perceive, yet it provides a consistent, predictable framework for understanding and harnessing that strangeness. It is a cornerstone of quantum theory, a bridge between realms, and a window into the hidden depths of reality. Superposition teaches us that beneath the calm surface of classical physics lies a dynamic landscape of possibilities, where the quantum world continuously shapes the universe we experience every day. At the frontier of quantum physics lies one of the most profound and mysterious principles ever discovered, the uncertainty principle. First formulated by Werner Heisenberg in 1927, it reveals a limitation in nature that is not due to experimental flaws or technological shortcomings, but is intrinsic to the universe itself. The uncertainty principle challenges our deepest assumptions about measurement, prediction, and determinism. In a documentary-style exploration, we delve into this fundamental idea, examining how it forms a critical link between the classical and quantum worlds, reshaping our understanding of reality in ways both subtle and profound. In classical physics, it was assumed that if we could measure an object's position and momentum precisely enough, we could predict its future with absolute certainty. A planet's orbit, a falling apple, or the trajectory of a projectile could, in principle, be calculated exactly. The universe was deterministic. Knowing the present meant knowing the future, but at the quantum scale, Heisenberg discovered that this assumption fails. Particles, such as electrons, do not allow simultaneous exact knowledge of certain pairs of properties. The more precisely one measures the position of a particle, the less precisely one can know its momentum, and vice versa. This is not a limitation of measurement instruments. It is a fundamental feature of the quantum world, built into the very fabric of reality. The implications of the uncertainty principle are staggering. At first glance, it appears as a mere technical restriction, a detail relevant only to tiny particles. But it represents a deep departure from classical thinking, showing that nature itself does not provide absolute determinacy at small scales. Unlike classical physics, where uncertainty comes from ignorance or imperfect tools, quantum uncertainty is unavoidable. It reveals that the universe is probabilistic at its core. This means that, at the microscopic level, reality is not a set of fixed, predictable outcomes but a tapestry of probabilities, constantly fluctuating and evolving according to precise statistical laws. One of the most famous illustrations of the uncertainty principle comes from the behavior of electrons in atoms. Classical physics would predict that electrons, orbiting a nucleus like planets around a sun, could have well-defined positions and velocities. But according to quantum mechanics, electrons cannot have both simultaneously. Instead, they occupy clouds of probability, regions where they are likely to be found. The uncertainty principle is the reason why these clouds exist. It prevents electrons from collapsing into the nucleus, creating the stability that makes atoms, and therefore all matter, possible. Without this inherent uncertainty, the universe as we know it would not exist. It is a fundamental rule that underpins the very structure of reality. The principle also imposes limits on how precisely we can observe nature. In laboratory experiments, attempts to measure an electron's position more accurately require interactions with photons of increasingly high energy. But these interactions disturb the electron's momentum, making precise knowledge of that property impossible. The act of measurement itself becomes intertwined with the object being measured. In this way, the uncertainty principle connects deeply with other quantum phenomena, such as superposition and wave function collapse, reinforcing the idea that observation is not passive. It shapes the reality we observe. The universe at the quantum scale is interactive, dynamic, and inherently uncertain. Despite its strange implications, the uncertainty principle has practical consequences that are profound and far-reaching. It explains why quantum systems exhibit fluctuations in energy even at absolute zero, a phenomenon known as zero-point energy. It underlies the behavior of semiconductors, which form the basis of all modern electronics, and it governs the limits of precision in instruments such as atomic clocks and electron microscopes. The principle is not merely theoretical. It dictates the possibilities and constraints of technology, chemistry, and physics at the smallest scales. At larger scales, the uncertainty principle seems less noticeable, because the effects of quantum fluctuations average out over countless particles. A baseball, a bridge, or a planet behaves as if classical physics is perfectly accurate. Yet at the microscopic level, uncertainty is unavoidable, and it defines the boundary between the predictable classical world and the probabilistic quantum world. This boundary, this bridge, is where the uncertainty principle operates, mediating the transition from classical determinism to quantum probability. It shows us that classical laws are emergent, reliable at large scales, but ultimately founded on a foundation of quantum uncertainty. Philosophically, the uncertainty principle forces a profound reconsideration of determinism and causality. It challenges the Newtonian world view, suggesting that the universe is not a clockwork mechanism whose future is entirely predictable. Instead, it is a dynamic system where probabilities reign, where outcomes cannot be known in advance with absolute certainty, and where chance is built into the essence of reality. This realization opened the door for the development of new theories such as quantum field theory, quantum information, and even quantum cosmology, each relying on the probabilistic nature of the quantum world. The uncertainty principle stands as a central pillar in understanding the quantum classical bridge. It explains why quantum behavior dominates at microscopic scales, while classical laws emerge for macroscopic systems. It provides insight into why nature can appear predictable on human scales while remaining fundamentally indeterminate beneath the surface. In essence, it is the rule that allows the universe to be both ordered and unpredictable, coherent yet probabilistic, deterministic in appearance, but inherently uncertain at its core. In the grand narrative of physics, the uncertainty principle marks a turning point, a revelation that the universe is not simply a machine to be measured with infinite precision. It is a living, dynamic system governed by probabilities and possibilities, where measurement, observation, and interaction are inextricably linked. By defining the limits of knowledge, the uncertainty principle bridges classical and quantum worlds, offering a profound insight into the structure of reality. It teaches that the universe is more subtle, more intricate, and more beautiful than the rigid certainties of classical physics ever suggested. It is a principle that captures the essence of the quantum revolution and continues to shape our understanding of the cosmos today. As the quantum revolution unfolded, scientists faced the task of connecting the strange, probabilistic world of particles to the smooth, predictable reality of classical physics. One of the most profound bridges in this endeavor is the concept of quantum decoherence. Decoherence explains why quantum superpositions, which allow particles to exist in multiple states simultaneously, seem to vanish as systems grow larger, giving rise to the classical world we experience. In a documentary-style exploration, we journey into this hidden process, revealing how interactions between particles and their environment gradually suppress quantum behavior, creating the familiar, deterministic universe around us. Decoherence is not just a theoretical curiosity, it provides the crucial link between the microscopic and macroscopic, helping us understand why quantum rules dominate small scales while classical laws govern large systems. At the heart of decoherence is the realization that quantum systems are rarely, if ever, isolated. In the lab, an electron or atom can be prepared in a carefully controlled superposition, but in nature, particles constantly interact with their surroundings. Air molecules, photons, electromagnetic fields, and other particles continuously nudge and probe quantum systems. Each interaction entangles the quantum system with its environment, spreading quantum information and effectively measuring the system in countless ways. The result is that the delicate superpositions that allow a particle to occupy multiple states simultaneously are disrupted. The once coherent wave function begins to break apart, and the probabilities associated with each state effectively collapse, giving the appearance of classical definiteness. Decoherence explains a puzzle that has long perplexed physicists. Why do macroscopic objects, composed entirely of quantum particles, behave in ways that seem completely classical? A chair, a planet, or even a human being contains an enormous number of quantum constituents, each capable of existing in superposition. If these particles could maintain their quantum states collectively, macroscopic objects would appear to exist in multiple positions or states at once. Yet we never observe such phenomena. Decoherence shows that interactions with the environment are so rapid and pervasive that any superposition at large scales becomes essentially impossible to detect. Classical reality emerges naturally from the collective behavior of countless entangled particles, their quantum properties averaged out by the environment. This process also clarifies the connection between quantum measurement and the apparent collapse of the wave function. When a particle is measured, it becomes entangled with the measuring device and, indirectly, with the surrounding environment. Decoherence spreads the particle's quantum information into a vast network of interactions, making the superposition states practically inaccessible and producing a single observable outcome. This mechanism preserves the probabilistic nature of quantum mechanics, while explaining why classical outcomes appear definite. In essence, decoherence shows that the boundary between quantum and classical is not a sharp line, but a gradual transition mediated by environmental interactions. The implications of decoherence extend beyond theory into practical technology and experimental physics. Quantum computers, for instance, rely on maintaining coherent superpositions of qubits to perform calculations exponentially faster than classical computers. Decoherence poses a major challenge in these systems, as interactions with the environment destroy superpositions and limit computational efficiency. Understanding and controlling decoherence is crucial for advancing quantum computing, quantum communication, and quantum sensing. Experiments with ultra-cold atoms, trapped ions, and superconducting circuits all explore ways to isolate quantum systems and prolong coherence, demonstrating both the power and fragility of quantum behavior in the real world. Decoherence also reshapes our philosophical understanding of reality. It challenges the classical notion of an objective, observer, independent world by revealing that the apparent definiteness of macroscopic objects emerges from interactions rather than being intrinsic. The universe at its fundamental level remains probabilistic, with uncertainty and superposition governing microscopic processes. The classical world is a kind of emergent illusion, stabilized by decoherence, where the chaotic quantum possibilities of tiny particles are averaged into predictable patterns. This perspective bridges the quantum-classical divide, showing that classical determinism is an emergent property of quantum laws, not a separate set of rules. In addition, decoherence provides insights into long-standing quantum paradoxes. Schrödinger's famous thought experiment, in which a cat is simultaneously alive and dead, illustrates the tension between microscopic superpositions and macroscopic definiteness. Decoherence explains why such macroscopic superpositions are never observed. Interactions with the environment force the system into definite outcomes almost instantaneously. The cat is never truly in a liminal state, because the quantum coherence that would allow such superpositions cannot survive at large scales. This makes the classical world reliable, predictable, and consistent with everyday experience, while preserving the counterintuitive principles of quantum mechanics at small scales. The study of decoherence has transformed the way scientists understand the quantum world. It shows that the classical reality we take for granted is deeply connected to the underlying quantum structure of the universe. It is not a separate realm, but an emergent phenomenon arising from countless microscopic interactions. Decoherence explains why quantum strangeness is hidden in everyday life, why probabilities govern electrons and photons but not baseballs and planets, and how the bridge between the quantum and classical worlds is formed naturally through environmental entanglement. Ultimately, decoherence is a profound reminder that the universe is both layered and interconnected. It links the invisible quantum realm, where superpositions, entanglement, and probabilities dominate, to the familiar, stable classical world we inhabit. By revealing how interactions with the environment enforce classical behavior, decoherence helps us understand why nature appears deterministic and predictable at large scales while remaining fundamentally probabilistic at its core. It is a bridge between worlds, a hidden process that shapes reality, and a principle that continues to guide research, technology, and our understanding of the universe at every scale. As the journey from classical to quantum physics reaches its culmination, the focus turns to the profound implications of quantum theory for our understanding of the universe as a whole. This keynote examines how the principles of quantum mechanics, including superposition, entanglement, uncertainty, and decoherence, have not only transformed the microscopic world but also reshaped our view of reality itself. The classical universe, once seen as predictable, deterministic, and fully knowable, is now understood as an emergent approximation of a deeper, probabilistic structure where possibilities coexist, and the act of observation plays a fundamental role. In this exploration, we uncover how quantum principles bridge the gap between what we can directly perceive and the hidden processes that govern the fabric of existence. At the heart of this bridge lies the recognition that reality is layered. Classical physics describes the macroscopic world, where objects have definite positions, velocities, and trajectories. It explains the motion of planets, the flow of fluids, the behavior of machines, and the patterns of everyday life. Yet, beneath this apparent solidity, the quantum world operates according to different rules. Particles exist in superpositions of multiple states. Properties like position and momentum are constrained by uncertainty, and particles can become entangled across vast distances. Decoherence explains how these quantum behaviors average out to produce the deterministic classical reality, yet the underlying quantum layer remains ever present, shaping the possibilities of matter and energy at all scales. One of the most striking features of the quantum universe is entanglement, which demonstrates that particles can be instantaneously connected, no matter how far apart they are. This phenomenon challenges classical notions of locality and independence. Two entangled particles behave as if they are part of a single, inseparable system, with measurements on one instantaneously influencing the other. Such correlations are not mediated by any known force in the classical sense, but are instead a fundamental feature of the quantum fabric. Entanglement illustrates that the universe is deeply interconnected at a level hidden from everyday perception, and it underlines the idea that classical separateness is an emergent property rather than an absolute truth. Superposition adds another layer of complexity, showing that particles can occupy multiple states simultaneously until observed. This principle challenges the classical notion that objects possess definite properties at all times. In microscopic systems, superpositions are readily observable, such as electrons existing in multiple orbitals or photons in combined polarization states. These possibilities collapse into definite outcomes upon measurement, creating the appearance of a deterministic world at larger scales. Superposition is thus both a tool for understanding quantum systems and a window into the underlying richness of reality, revealing that the classical world is constructed from countless overlapping possibilities that are constantly interacting and resolving into definite states. The uncertainty principle further reinforces this layered view. At the quantum level, certain properties cannot be simultaneously measured with arbitrary precision. Position and momentum, energy and time are constrained by fundamental limits that prevent the kind of absolute determinism assumed in classical mechanics. This intrinsic uncertainty is not a limitation of instruments or knowledge, but a fundamental feature of nature. It ensures that the quantum world is probabilistic, that particles explore ranges of potential behaviors, and that outcomes are governed by statistical laws rather than strict causality. Yet, at macroscopic scales, the collective effect of countless particles averaging out these uncertainties produces the smooth, predictable world described by classical physics. Decoherence completes the picture by explaining why macroscopic objects appear to behave classically despite being composed of quantum particles. Interactions with the environment cause quantum superpositions to degrade rapidly, forcing systems into definite states that align with our everyday observations. This natural transition from quantum possibilities to classical definiteness forms the bridge between worlds, allowing the probabilistic rules of the microscopic universe to produce deterministic, reliable patterns we perceive. The classical world is thus an emergent property, stabilized by countless microscopic interactions and shaped by the invisible quantum landscape beneath it. The implications of this understanding extend far beyond physics. In technology, quantum principles have enabled the development of computers, cryptography, lasers, and sensors that exploit entanglement, superposition, and coherence. In philosophy, quantum mechanics challenges long-held assumptions about determinism, separateness, and objectivity. It forces us to consider a universe in which observation, interaction, and probability are central, and where the line between possibility and reality is far more fluid than previously imagined. Quantum theory reveals that the familiar world is only a surface manifestation of a deeper, richer order. In contemplating this bridge, one realizes that classical physics is not wrong but incomplete. Its laws are approximations that emerge from the underlying quantum framework, accurate at scales where quantum effects average out. The quantum world, however, operates independently of our perceptions, following principles that are stranger, more interconnected, and more probabilistic than classical intuition allows. The bridge between these realms is not a single formula or experiment, but a continuum of understanding that connects microscopic uncertainty and macroscopic predictability, showing how the classical universe arises from quantum foundations. Ultimately, the study of quantum mechanics reveals a universe both familiar and profoundly strange. The everyday world operates according to classical laws, providing stability and predictability, yet beneath it lies a realm of probabilities, connections, and possibilities that shape every particle, atom, and molecule. This hidden quantum reality forms the true foundation of existence, and understanding it allows us to appreciate how classical and quantum worlds are not opposed but deeply interwoven. The bridge between them is a testament to the elegance, complexity, and subtlety of the cosmos, a reminder that reality is layered, interconnected, and infinitely richer than what our senses alone can perceive. It is here, in this intersection, that science continues to expand the horizons of human knowledge, revealing a universe that is at once comprehensible, mysterious, and endlessly fascinating.